Okay, we have our midterm exam on Wednesday, right? The midterm will cover pretty much everything that we've done, but not this, right? Not 11.8, but I said I would start 11.8 today. I gave you some problems to review, to go back and take a look at, but you should be looking at your homework problems. You should be looking at the problems that I did in class. And you should be all right on the midterm. Remember, the policy that I have in the syllabus about the midterm and the final, you must score 50% or higher on the midterm or final to pass this class. So if you score below a 50 on the midterm, you automatically have an F in the class, and that's it for you. Okay, that's because people have been asking me, like, why do I have that policy? The reason is because everything that you've been doing is take home. So there's really no way of me knowing who's doing it. Like, I trust that everyone has integrity, that you're doing your own work. But if you're turning in, good grades on all your take-homes, and then you come in, you get a 20 on the midterm, then I'm going to start to question whether or not that was really you doing all that work at home. So it's just so that there's some accountability. You have to at least know half of the material on the midterm, okay? But I don't want that to be a surprise either. If someone gets like a 40 on it, and I'm like, hey, you need to drop the class. I don't want them to be surprised. Okay? All right, so we are going to start 11.8. This is one of my favorite sections in the entire book. I'm not quite sure why I like this section so much, but I do. And it's going to be some algebra. There's going to be some algebra in this section that gets a little bit messy. But more importantly, what we have here is really one of the first times we really have to think like logically about trying to check whether or not things are true or false. And like, when do you know you're actually done checking? And so this is the first time you're ever going to see something like this. It's difficult to get thorough with this method. So I'm going to try and point out all these little things I'm talking about right now as we move through the examples. This is called Lagrange multipliers. It's the section. And it's just an absolutely wonderful result. So let me bring it up here. Okay, so far what we've done in the last section is that we know that we can find local maximums and local minimums of functions of two variables, right? Surfaces on their implied domains. And that's when we used capital D, right? Then at the end of the section, you had to go and try and find the absolute maximum or minimum of a function of two variables on some closed bounded region. So that's where you had to move along the edges, right? That's what we did last class? Yeah? Y'all okay? Hello? Is this working? My mic working? Okay. We now develop a very powerful method for finding the maximum and minimum values of a function subject to a constraint. So what does that mean? Subject to constraint. Well, here's the method. Here's the method, and then I'll show you a picture. So this is a method of Lagrange multipliers for two variables, meaning that we have a function of two variables, and we are given a constraint. Now, we're going to call this a constraint equation, and it is also, it has two variables in it. Okay, so you have some equation over here that involves two variables and a constant. If we want to find the maximum or minimum values of this function when we restrict ourselves to this constraint, then this is what we're going to have to do to figure it out. Do you remember when we were trying to find the local max and local min? We were finding, we set those partials. Remember we set the partials equal to 0? Do you remember that when we were computing D? We did this, we figured out what x's and y's made these both true, and then we calculated D, right? Took these points and calculated D. This method says we can still find these x's and y's, but what we're going to do to get them is going to be a little bit weird. Okay, what we're going to do is this. We are going to find all values of x, y, and the Greek letter lambda that make these two things true. First, the gradient of f must be equal to lambda, which is a constant, times the gradient of g. Do you all remember that the gradient vector, right, is a vector, yes? Gradient is a vector. This is a vector also. And if I'm saying that this vector is equal to lambda times this vector, then what can you say about these two vectors, the two gradients? They're parallel, right? That's what it means. They're scalar multiples of one another. So for some reason, the places we're going to have maximums or minimums of this function happen when the gradient of this function is parallel to the gradient of our constraint. I'm going to try and show this to you visually later. For now, you're just going to have to believe that it works. So we have to satisfy that equation, and we also have to satisfy the constraint. All right? We will evaluate the function at all the points that satisfy these two things. The largest is the maximum, the smallest is the minimum. Now, when we say that we need the gradient of f to be equal to lambda times the gradient of g, remember the gradient of f is just the partials? So this is the gradient of f. This is the gradient of g times lambda. So I passed the lambda through. We want these two to be equal, so what we do is we just set the components equal to each other. So it turns out, end of the day, okay, at the end of the day, when you're trying to figure out how to do Lagrange's method with two variables, you need to be able to satisfy three equations, and here they are. If you can satisfy those three equations, you're in business. And the end of the notes here, I remind you of what those three equations are going to be. Here they are. Okay? Y'all got it? This is what I'm about to use through the next few examples. When I have three equations, right, I'm also going to have how many variables? Three. What are they? X, y, and lambda. So I'm going to have three equations. I'm going to have three unknown variables. I need to find the solution set for that. And these are not necessarily linear equations. These could be nonlinear. So we can throw all the matrices stuff out the window. Okay, so let's get an idea visually what's happening. I want to find the maximum and minimum values of this surface, all right? So just by looking right now, if I don't restrict the domain and just let its domain be whatever its domain is, its implied domain, does this have a minimum value? Yes. Yes, it would be down there at the very bottom, right? What would be the maximum value? Well, I had to stop my picture. We have to imagine that this keeps going, right? So there would be no maximum, would there? Like if this thing just opened up forever? It would have a lowest point, but it wouldn't have a maximum. Yes? Okay, so f of x just by itself has a minimum value but not a maximum. But what if I just restrict it to this? What does it mean to constrain it? This is our constraint here. I'm looking at the maximum minimum values of that function just on x squared plus y squared equals 1. You recognize that? X squared plus y squared equals 1? It's a circle, right? That circle would live in two-dimensional space. It would be on the xy plane, right? In three-dimensional space, what's x, y, z? X squared plus y squared plus, x squared plus y squared equals 1. What's that in three-dimensional space? Cylinder, right? So what we're imagining is we're taking all the points that lie on that circle, right, on the ground, that's our domain, and we're just mapping those points into the surface, okay? If you're just allowed to plug those in, see, that's where we're constrained, our domain is constrained there. Then what we get is where that cylinder comes up and hits the surface, right? See the blue? That's where the cylinder hits the surface. And I can take the surface out of there completely. And so what we're looking for is the maximum and minimum values of this blue curve. Where do they happen, right? We have, it looks like 2 maximums, right? And 2 minimums. Where do they happen? That's the question. Understand? Where do they happen and what are they? Any issues visually with what's going on? No? We're good? Okay. Is that different than what we did last class? Are we finding the local max and mins on its implied domain? Are we doing that here? No, we're not at all. We are actually being very specific about its domain. And we are restricting its domain just to a circle on the ground. See how that's different than the capital D thing we did? Now, is it similar to the thing that we did with closed-bounded sets? Is it similar? Remember for a closed-bounded set? You have to have all the stuff inside and the edges? Is this a closed-bounded set? Is it? It's just the edge. Do you see that? So this is not what we did before. It's not the implied domain. It's not a closed-bounded set. This method's really good for finding the edge part of it, though. Understand? You good with that? Okay. We're about to see. Regardless of whether or not you understand the geometry of what's going on, let's see if we can do the math. So this is a function of how many variables? 2 variables. I'm subject to a constraint. I'm going to be using Lagrange's method, okay? Lagrange multipliers. Because I have 2 variables, I know I'm going to set up 3 equations, right? Equation 1, which I'm going to label 1, is going to be the partial of f with respect to x must be equal to the lambda times the partial of g with respect to x. By the way, what's the g function here? X squared plus y squared, just that part. Okay, the constant on the other side doesn't matter. G is the part that has the x's and y's. Just make sure, if this equation's weird, you've got x's and y's on both sides, make sure you move everything to one side, all right? Okay, so that's the first equation I have to set up and satisfy. The second equation, I'm going to erase that g thing from there. It's in my way. Is partial of f with respect to y must equal to lambda partial of g with respect to y. And then the third equation is what? It's the constraint equation, the whole thing. So now let's actually figure out what this is. What is the partial of f with respect to x? That's partial of this one with respect to x, which is 2x. That must equal lambda times partial of g with respect to x. What's the partial of g with respect to x? 2x, so lambda times 2x. All right, I'm going to kind of separate these. Okay, that's my first equation. My second equation, what's the partial of f with respect to y? 4y must equal lambda partial of g with respect to y, 2y. And then my third equation, I don't need to touch that, okay? That just has to be true. The reason why this has to be true is because that's what's going to keep me on the constraint, on the circle, right? All right, we have some equations here. Let's see if we can do some stuff first that we know for sure is legal. I can divide both sides here by 2, right? I get x equals lambda x. I can divide both sides here by 2. I get 2y equals lambda y. We comfortable with that? I'm working with these like that. Everyone good? Now, we need to find an x, a y, and a lambda that make all 3 of these true at the same time. So let me first try to see if I can figure out something from the first equation. So someone might say, well, divide both sides by x and you get lambda, right? But if you divide both sides by x, what are you also promising me? X cannot be 0, right? So you've eliminated one of the solutions. What did I tell you? I know I told you about this. Don't do that. I said what instead? Don't ever divide by a variable that you can't control. What did I say to do? Take it all to one side. So let's just move the lambda x to the other side. And now you can do what? Factor out the x, right? So if I factor out the x here, I get x, and I get 1 minus lambda equals 0, right? Okay. This is where I was telling you at the beginning of class. The part of these problems that gets weird, that you get points taken off for, is that you'll get answers, but then you forget that there was other stuff you were supposed to look at. So I'm just going to focus on that right now. Okay, this is my work over here. I'm going to start writing logical steps here. Okay, ready? What did I say this was? Oh, I forgot to set these equal to 0. Sorry. X equals 0. And then this, if I set that to 0, I get what? Lambda would have to be 1, right? So to satisfy the first equation, x would have to be 0 and lambda would have to be 1. Yes? All right, I have to look at both of those scenarios. So I'm going to start with the first one. Suppose that x is 0. What can you tell me if x is 0? That y squared must equal 1, right? So what I'm going to do is this. Suppose x equals 0. Then 3 implies, so I'm telling you now, to look at equation 3. If x is 0 there, that equation implies what? Y squared must be 1, which means y equals plus or minus 1. Agreed? Also, within this same framework, can you tell me what lambda would be? Because right now, here's what we have. We have x is 0, y could be 1, and then I'm going to do it this way, x, y, lambda. Okay, tell me, this doesn't live in three-dimensional space or anything. This just, I want to know the value of x, y, and lambda. I have that scenario, and I have this scenario. So let's see if we can figure out what lambda would be in this first one. If x is 0 and y is 1. So if x is 0, this is true, right? Okay, come over here. If y is 1, what would happen? From equation 2, what? 2y, I'm sorry, y is 1? Isn't y 1? Okay, so this would be 2 equals lambda? 2 equals lambda. So I could say that's 2, right? Understand that? How about this? If I assume that the y is negative 1, then what would 2 give me here? Negative 1, negative 1. We get negative 2 equals negative lambda, so still lambda's 2? You following me? So far from Lagrange multipliers, here's what I know. If x is 0, then y has to be plus or minus 1. If x is 0 and y is 1, then lambda's 2. If x is 0 and y is negative 1, lambda's 2. So these three should work, yes? Or these three triples, or these two triples should work. Okay. Done with that thought. That was x0. Now, let me suppose lambda's 1, because if lambda's 1, this is also satisfied, isn't it? So now I'm going to start a new thought over here. I'm going to erase this. Do you see how people might work through that? Get this out, get those points, and then be done? And then move on to the next problem and realize, look, you never checked lambda was 1. And that you'll lose points for. Even if you get the right answers, if you don't check all of them, that's a mistake. All right, so suppose now that lambda's 1. What would you like me to look at? If lambda's 1, can I figure out what x and y are? Well, what does the first equation turn into? If lambda's 1, go to here, right? Go to right here. If lambda's 1, then x is x, right? Does that help? X is x. Okay, so x can just be whatever it wants to be. All right, what about 2? Does 2 give us anything? That 2y is equal to what? y. Now that's different. X is obvious, right? Look, x is x. Everyone agree x is x? But that doesn't tell you shit, does it? 2y being y, now that's different. Subtract y from both sides. And what do you get? Y is, come on, we can do it. Subtract y on both sides. Y is 0. Now that's concrete information, right? Y is 0. The only time a number will be equal to double itself is if it's 0. That make sense? Okay, now if y is 0, now you have a little more information. What can you do? What can you conclude? Go to the third equation. What does the third equation tell you? That x squared plus y squared, which in this case would be 0, would be 1, right? And that means that x would have to be plus or minus 1. So now we have two other situations to look at. We know that x could be 1, y is what? 0, and lambda's 1. Or I could have x is -1, y is 0, and lambda is 1. Understand? This was all under the framework of lambda being 1. So this was always 1. When we worked through this, we knew y would have to be 0. And once we said that, that gave us two values of what x could be. So this is all within another thought. Got it? Okay. Are we done? We looked at this, right? Okay, what about this one though? What if you would have done the same thing that we did here for this one? Bring the y over to the other side. You would get 2y minus lambda y equals 0, right? Factor out a y. Get 2 minus lambda equals 0. You agree? And so we have two possible answers here. Y could be 0 or lambda could be 2. Well, guess what? We get to go look at those now. But one of them's actually not that bad. Because what if y is 0? Didn't we just do that? Didn't we just do that? But I'm gonna go through the process. Suppose y is 0. If y is 0, then the second, well, no. Y is 0. What can I say? From the third equation, this is true. So I'll say from the third equation, I know that x must be plus or minus 1. Agreed? So I have this right now. I have y is 0. X could be 1. X could be -1. Do you see I'm repeating myself? I've actually done this work. But is our lambda going to be any different? If x is 1 and y is 0, what's lambda? Try it out over here. X is 1, y is 0. How about this? X is 1. What do you get? Lambda's 1, right? Doesn't that match what we just did a second ago? Yes? Back when we let lambda be 1? And then what about if x is -1 and y is 0? -1, -1, you get -1 is equal to negative lambda. That's also 1, right? So I've repeated myself. If this were a test or something, I wouldn't expect for you to necessarily go through this again, but I would expect for you to write this down. And then down here, you could just be like, okay, we already took care of that, right? All right. But what we have not done is looked at lambda being 2, have we? You ready to see lambda 2? Suppose lambda is 2. Or did we do that? Did we get lambda 2 earlier? Yeah. We did. Okay, so when lambda was 2, that's when we had x was 0, didn't we? So go back and look. Lambda 2, see previous work. We had 0, 1, 2, and 0, -1, 2. Is that right? Yeah. Is that what we had earlier? Okay. So we've already done this. You got it? So at the end of the day, there are four pairs of x and y coordinates we need to look at. The lambdas are not important when we're going back and trying to figure out where the max and min are. The lambdas are important for us to be able to solve the equations. We need 3 variables to solve for 3 unknowns. So this is just part of us getting x and y. So we are now going to look at and compare the following. We have to look at f of 0, 1, f of 0, negative 1, f of 1, 0, and f of negative 1, 0. Right? Those are the x's and y's that we had without the lambdas. What's f of 0, 1? Going back into this function. 2. What's f of 0, negative 1? 2. F of 1, 0, 1. F of negative 1, 0, 1. So this right here corresponds to our minimum. And this, because they're the same numbers, this is our max. So what is the maximum value of this function if we constrain ourselves to that circle? What's the biggest value it ever attains? 2. And it happens at 2 different x and y values, right? If x is 0, y is 1. Yes? And then the smallest it'll ever be would be 1. Does that make sense? Okay. That was the easy example. This one's still easy. So look at this one. Find the maximum and minimum values, or minimum, of this function. Same function, right? What's different? It's an inequality instead of an equation, which means now you're looking at the entire disk, right? Your domain is now, everything on that disk can get plugged in, right? Not just the edge, everything. Lagrange allowed us to do the edge, right? We still need to do the inside pieces now. How do you think we can do the inside pieces? With the capital D, right? Actually, we don't need the capital D. We just need the method, which was to set the partials equal to 0. Remember, when we set the partials equal to 0, this gives us candidates to get plugged into D, right? But from last class, we learned that, look, if we figure out where these happen, and then if we have to move along the edge, what we do is just compare all these answers. Make sure that these points live in our disk, and then from there compare. Now, what does this look like geometrically? What's different? When you compare that, you see the difference between this and the previous problem? Previous one was just moving along this edge. Now we're allowed to have all that junk in the middle. So when we look at it from the top, it should look like a circle. Okay, so this is going to have a maximum. Yes? Should be the same 2 maximums we had before, right? But the minimum is no longer these 2 points, right? It's this point. So how do we find that? Well, we just set the partials equal to 0. So all we're doing is just adding one more layer onto this problem, right? We've already done the edge. Now let's do the inside. So just set partial of f with respect to x equal to 0. This is going to be a very simple one to solve. What is it? 2x equals 0. What's the solution here? X is 0. So that's how we set the first partial equal to 0. Now you do the partial of f with respect to y equal to 0. That's 4y equals 0. And so y equals 0. So the only way to get the 2 partials here equal to 0 is to let x be 0 and y be 0, which gives us a point 0, 0. So you remember just a second ago when we did Lagrange, we did 0, 1, 0, negative 1, 1, 0, negative 1, 0. Now we have one additional point to check, 0, 0. Understand? So this was all Lagrange. This is the thing from here. And when we plug in 0, 0, we get 0. And that's now our new minimum, right? These are no longer your minimums, because those came out to be 1s. That's it. Nothing else on that one. Okay? Questions?
So we always have to check those four and then before we get to our equation?
Say again?
Do we always have to check those four first and then whatever we get from the new equation?
Oh, no, you can do them all at one time. You could do the other one. Everything is going to be dictated by what your domain is. What is your restriction? If your restriction is just along an edge, a boundary, Lagrange, right, is all you'll use. If it's the boundary and everything inside, then you'll need to use some combination of both, or do what we did last class where you just like do L1, L2, and move around the edges. If there's no restriction on the domain, then you have to do capital D to get local max, local min. And that's all you're doing is finding local, not global. Is that kind of clarified a little bit? Okay. All right. We're going to do this one. We'll look at it in a minute. All right. Again, please pay attention to organizing our thoughts properly, taking the different scenarios. Find the maximum and minimum values of the function f of xy equals 4x plus 6y with the constraint that x squared plus y squared is 13. I will have how many equations that I need to satisfy here? 3 equations. The first one is partial of f with respect to x must equal lambda partial of g with respect to x. The next equation, partial of f with respect to y must equal lambda times partial of g with respect to y. The third equation is the constraint, x squared plus y squared must equal 13. And keep in mind that what I circled in blue there, that's g, right? Aren't we plugging in just points on a circle again, just on the edge? And we're plugging those into this function. Anyone know what this function draws? It's a plane. That's right. It's a plane. That's the same as saying like z equals 4x plus 6y. Everything's linear. All the variables are linear. You should draw a plane. All right, well, here we go. First equation, partial of f with respect to x. Oh, that's clean, right? 4 equals lambda times partial of g with respect to x. So partial of this with respect to x is 2x times lambda. So can I write 2 lambda x? All right. What's the next one? Give me the next equation, someone. 6 equals 2 lambda y. Okay, good. And then the last one, there's nothing to do. Let's scale through just to clean them up a little bit. This is 2 is equal to lambda x. This is 3 equals lambda y. And I'd say those are probably the cleanest versions of the equations I have, right? Now what? Any requests? Last time I moved everything to one side, right, and factored, set equal to 0. Can't do that this time. Any ideas? Somehow set them equal to each other? Okay. How? Substitute? Yeah. How? You want to solve one of them for lambda and then maybe plug that into the other one? Or you could solve them both for lambda, couldn't you? And set them equal to each other? Yes, right? Everything is, you're free to do algebra at this point. You just have to be careful. So let's solve for lambda, okay? Let me solve for lambda. And let's do equation 1. And I'm going to do my work right here. I'm going to take equation 1, and it implies that 2 over x equals lambda, right? But I just did something. What did I do? Divided by x. So I need a little disclaimer in here. I need to let everyone know that the only way that that's happening is if x isn't 0, right? So before I start this, I'm going to say, suppose x is not 0. What do you think that means we're going to need to do when we're done here? Go back and say, well, what if x is 0, right? And if you forget to do that, then you're missing part of the problem, all right? I can only divide both sides of that by x if I assume x is not 0. Understand? Suppose x is not 0, then lambda's that. Then what? I can go to the second equation. I can go to the second equation, and I can replace my lambda with what? 2 over x. So I get from my second equation that 3 equals 2 over x times y. You with me? Solve this. What do you get here? How are you going to solve this? What are you going to do? I don't know what you're going to do. You could divide by 2, yeah?
Common denominator?
Okay, why don't we, are you trying to get rid of this x over here? Like make it cleaner, like get rid of it? Or
I was thinking about moving the 3 to the other side and then getting 3x over x, putting it together as one fraction. Down in the bottom can't be 0, solve the top for 0.
I see what you're saying. Yes, we can do a common denominator right now. Here's something I would suggest. I could clear this fraction out by multiplying both sides by x, right? Now the danger in that is that what if x was 0, right? X isn't 0. So I can clear fractions, multiply both sides by x right now, which is probably what I would do here. What I'm creating is a relationship between x and y. Why am I creating a relationship between x and y? What am I going to do with this relationship? If I know somehow x and y are related, like for example, I know that x is equal to 2/3 y, then what can I do from that? I can go to my third equation now. I can replace x with 2/3 y, and now I've got one equation that has just y's in it, don't I? So let me do that. The third equation now becomes what? This is x, right? So it becomes 2/3 y, that's x squared, plus y squared equals 13. Don't forget to square the fraction here. So this is 4/9, continuing here, 4/9 y squared plus y squared must equal 13. And then go ahead and continue on. How many ninths y squareds do we have now? 13/9. 13/9 y squared equals 13. What about multiplying both sides by the reciprocal? Get like y squared is 9, which means y is plus or minus 3. So as long as x is not 0, y is going to be plus or minus 3, as long as x is not 0. Right? What can we do once we know what y has to be? Come back and where is it? Where's x? Oh, this is x, right? X is 2/3 y. So once I know what y is, I'm going to come back and get x now. So that implies, I'm continuing all this. I'm just running out of room. That implies that x is equal to 2/3 times, I could say plus or minus 3. I hope that that makes sense to you. So plus or minus 2. Now we have to be kind of careful with this, all right? Because if y is positive, x is positive, right? If y is a positive number here, x is positive. If y is negative, x is negative. So the way I'm actually going to write this is as follows. Here's what I've got. I could have x be 2, and y would then be, what is it, 3? Or I could have -2 and -3. You follow? Where's my y? If y is positive 3, plug positive 3 in here, we get x is 2. If y is negative 3, plug it in here, we get x is negative 2. Yes? What I want you to be careful with is this. We are not saying this. This would not be okay, would it? That would not be okay. Because, look, if y is 3, is x negative 2? No. So just be careful with what we're saying when we're solving these. It's not just like, just because you see plus or minus doesn't mean every combination you could think of. They actually connect together sign-wise. All right, what am I still missing here that I haven't got? The lambdas, right? The lambdas. So let's see if we can get a lambda. Did we ever solve for a lambda? Oh, yeah, we did, right there. There it is. Okay, so if lambda is 2 over x, in this case, it would be 2 over 2, which means lambda is 1. And then same thing for this one, it would be negative 1, wouldn't it? Okay, we're done with that. That's what happens if x is not 0. What should we look at next? What if x is 0? We never looked at that, did we? Okay. So let me change this. Suppose x is 0. Now you can't solve for lambda, can you? If x is 0, what can you tell me? Y squared equals 13, right? But you've got another problem. Look at your first equation. If x is 0, what's your first equation say? Equation 1 says that 2 is equal to 0, right? And it's not. Which means x can't be 0, okay? But you had to think about it, because if you just, I heard someone say it, and that's okay. If x was 0, yes, it would imply that y is going to be, what, square root of 13 plus or minus? But see, x being 0 does not satisfy this equation. It has to be all three simultaneously. Okay. Anything else that we didn't look at? What about taking equation 2 and solving it for lambda, and then taking that and plugging it into this one? So what would I have to start my suppose off with? Suppose y does not equal 0. Right? If y does not equal 0, I can take my second equation and divide through by y. So that would get 3 over y equals lambda. And then I could plug into equation 1 with that. And my equation would be 2 equals 3 over yx. Starting to look a little familiar. This is what we did just a second ago. Clear the fractions. We get 2y equals 3x. And then I can solve this for x or y. I'm going to solve it for x. 2/3 y equals x. Isn't that the exact same thing we had earlier? Yes. Isn't this the same exact thing? So this is going to, from here on, it's going to be the same result. Right? Same result. We're going to have this right here. Because you're going to replace x squared with 2y, or 2/3 y. And then you're going to square it, and it's going to become 4/9 y squared, and you're going to move through the same thing, right? Okay. Is there anything else? You're going to have to do some jumping jacks or something. Yeah. Come on. Just go walk around or something. Is there anything else that I have not addressed or have not looked at?
Y is 0. Y is 0.
If y is 0. So yeah, what if y is 0? Suppose y is 0. Then what? Equation 2 says 3 is 0. That doesn't happen, so y can't be 0. If you do this, you can do that symbol right there. Just means contradiction. if y is 0, you get a contradiction. You're saying that 3 has to be 0, and that doesn't work. So these are two arrows hitting each other like that. Okay. See, this is where this is the part that makes this difficult, is have we covered all the different possibilities? Yeah, I think so. Oh, you know what? Could we solve this for x and solve this for y? Could we? Okay, so suppose what? If I'm going to do that, then I need to suppose what? Suppose lambda is not 0. All right? Suppose lambda is not 0. What would equation 1 tell us? X is 2 over lambda? Yes? What would equation 2 tell us? Y is 3 over lambda. You with me? Got it? Keep going. What now? Plug them both into 3. So go into equation 3 now. What's x? 2 over lambda. Square it. What do you get? 4 over lambda squared. Plus, plug y into this. What do you get? 9 over lambda squared equals 13. All right, put these together. You get 13 over lambda squared because they have the same denominator. And now just multiply both sides by lambda squared, which we can do because lambda is not 0. So you'll get lambda squared is 1, which means lambda is plus or minus 1. Have we done that? We actually did that already. Look at. See, you could almost look at this as in, look, those are all the, this is like, what if you had just started with this, said, hey, let's just assume lambda is not 0 and solve for x and y. You could have started the whole problem like this. And then you would have got lambdas plus or minus 1, and then you would have from that been able to come back and get what x and y were. So, I mean, there's just so many different ways. It's hard to finally get to a point where you're like, yes, I've checked everything. I've covered all the bases. Done this, all right? I'm just going to put done. We've checked that already. Anything else? Suppose lambda is 0. Contradiction, right? If lambda is 0, either 1 or 2 are going to be a contradiction. So lambda can't be 0. I'll put it down here. Suppose lambda is 0. Then this is the same thing, isn't it? Okay, that's it. It was a little more involved than the last problem, right? Yes?
Do you prefer solving it one way over the other?
No. My preference is that you cover everything you need to cover, and it doesn't matter which way you do it. I don't like grading these. It's very difficult to grade these. So I am looking for logical steps. You notice how I'm like bracketing out each of my, like suppose, bracketing it. The next problems are going to get even more challenging. And so what we're going to have is like within one suppose, we're going to have another like 2 supposes that break off to be like 2 more supposes. So we're going to have like these branches of ideas. And that's what I hope to see from you, is some sort of logical structure, not just random, algebraic crap all over the place. Because if you over here suppose y is not 0, and then over here you suppose y is 1, those things, am I supposed to guess, like, are they together, like y is not 0 and 1, or are you trying to let y be 1 and 0 at the same time? You have to get it all in order. If you try and do too much at one time, and you're not, I don't know how to explain this. If you get lost in the problem, you might potentially be trying to let a variable take on 2 different values at the same time, which would be a disaster. All right, so I just erased the important numbers. What were they? I need to check f of 2, 3, 2, negative 3. That's it, right? Or negative 2, negative 3. That's it. Check. Most likely, that's going to be your max and min right there. One of those is going to give you a max, one of them is going to give you the min. So 2 goes in, 26. The other one, negative 26. I think it's probably obvious that that's going to be your max and min right there. Questions? Here's the picture. Here's the plane. Here's the restriction. On the ground, there's the restriction. Can you all see it? Here's the points from the restriction plugged in. And you can see where it hits the surface, right? And we just found the 2 points here. One of them up here is 26 units high. The one down here, 26 units low. Yes? All right. Now we're getting into some nastiness. E to the xy is our function. Here are our constraint. Here's our constraint. X cubed plus y cubed equals 16. We should have Lagrange multipliers for sure because this is an equation, right? Constraint equation. We're not given an unrestricted domain, right? We're not given a closed bounded set. This is just a curve, really, right, on the ground. So 3 equations. Partial f with respect to x equals lambda partial g with respect to x. Second equation. Partial f with respect to y equals lambda partial g with respect to y. Third equation. Constraint. X cubed plus y cubed equals 16. Once I set up the equations, I get to go solve them. So what is the derivative of f with respect to x? Y e to the xy equals lambda times the partial of g with respect to x. 3x squared, but then times lambda, right? So how about I write 3 lambda x squared. See, if you mess the partials up, it's over, right? I mean, pretty much at that point, it's done. All right, the next equation is partial f with respect to y, which is x e to the xy. And then partial g with respect to y is very similar to what we just had, except 3 lambda y squared instead of x squared. And then our third equation is there. All right. Enjoy. What do you want to do? Find an x, y, and a lambda that make all 3 true at the same time. For those of you who've studied matrices and linear equations, systems of linear equations, we understand that there's a very systematic approach to solving systems of linear equations. It's called Gaussian elimination. Computers are really good at it because it's just do this, just operations, addition and multiplication. That's all it is. Systems of nonlinear equations, much more difficult to do. And you have to do them by hand and check a lot of different scenarios. So, all right, what do you want? You want to solve? I heard solve for what?
We could solve for x or y, as we know that e to the x and y cannot be 0.
Yeah, but that's not equal to 0.
But if we divide by e to the x to the y.
Okay, you want to divide both sides by e to the x to the y.
That's what I'm saying.
Because you know that that will never be 0.
Right.
That's fair. We could do that. You want to divide both sides by that? Okay. I have no problem with that. Let's do it. So you want to divide. What's being suggested here, but hold on. Let me ask you before you put your pencil to paper on this. That's what I would get, right? But that's solved for y, but it's in terms of y still, right? Like to know what y is, you have to know what y is. You could solve for e to the xy on both of them. Or say again?
On both of them.
Solve both for e to the xy. I heard let's solve for lambda. They're both good. Do you understand the difficulty here? If you solve this for y, you haven't really solved it for y. Because you still need to know what y is to know what y is. Right? Like if I have like x equals 4 plus 1 over x. Have you solved for x? In order to know what x is, you have to know what x is, right? So all right, so let's take a vote. Are we going to solve for e to the xy on both? Or do you want to solve for lambda on both? E to the xy? Lambda? Okay, let's show hands because I can't tell by how many. Okay, how many of you want to solve for lambda? Okay, e to the xy. Wow, that's close. That's close. Okay, we'll go to the coin flip. So no distinguishing marks. That's heads. Heads is lambda. Sorry. Heads was lambda. I should have called that. It's like the Super Bowl flip. Okay. It's going to be lambda. We're going to go for lambda. All right. Yeah, it didn't flip. All right. So if I'm going to take equation 1 and solve for lambda, then what do I need to say? Suppose x isn't 0. Suppose x is not 0, right? Equation 1 becomes that, right? Now, what would you like me to do with that? You plug it into 2? Or we could solve the other one for lambda also and set them equal to each other. I'm just going to go right to 2 in this one. Although setting them equal would be the same. But I will say this. If you solve the second one for lambda, you're going to also have to tell me what? Suppose y is not 0. So you're fixing them both then. I'm going to stick with just, right now, the only condition I have is that x can't be 0. That's the only thing I'm saying. All right, so let me rewrite this now. I might, at the end of the day, have to say that y can't be 0 either. But 3, here's lambda. Lambda is y. E to the xy over 3. Oh, I like that. It's going to cancel. And then y squared. Did y'all see that Diaz fight? That Conor McGregor-Diaz fight? All right, there we go. That I can do, right? Cancel those. What else could I do to make this a little bit nicer? Can I clear the fraction? Can I multiply both sides by x squared? Yes, because I'm saying x can't be 0, so that's a legal move. Right? If x is 0, then I could potentially multiply both sides by 0, and you never want to multiply an equation by 0 on both sides. But x isn't 0, so this becomes x cubed e to the xy equals, what's over here? Y cubed e to the xy. Now what? You can divide out e to the xy now. I just told you, don't ever do that with a variable, but we all know that e to any power can never be 0, right? So I can divide this out safely without any concerns.
You see that I was seeing this.
Yes. Which means x cubed equals y cubed. X cubed must equal y cubed. So far, that's what I've got. If x is not 0, then to satisfy things, x cubed has to be y cubed. Now, where can I go from here? The third equation. In the third equation, that would imply that, which one do you want to replace? You want to replace that with y cubed or this with x cubed? Doesn't matter, right? So I'll replace x cubed with y cubed. Oh, look how nice this is going to be. 2y cubed equals 16, which means y cubed is 8, which means y is 2, not plus or minus, right? Just 2? All right. Now what?
Is it going to be plus or minus or just plus?
Just plus because it's a cube, not a square. That means x is 2 because of this equation, right? Which implies that x is 2. Hey, this is promising. I've got 2, 2 so far, right? Can you give me what lambda would be in this case? Do we have an equation with lambda in it? Right here. Replace your y with 2. It would be, I'm telling you how I'm getting lambda here. 2e to the 4 over 3 times 2 squared, which is e to the 4 over 6. Whatever that is, who cares what it is. But there is a lambda, e to the 4 over 6. Everyone understand? All right. I'm only putting my marker away because it's starting to die a little bit. Am I done? What else do I need to look at? That was just saying that x wasn't 0. That's what happens, right? That's because y'all wanted to, well, no, the ruler wanted us to go and solve for lambda. So maybe we should check before we forget that, what happens if x is 0? What if x is 0? Are we going to run into any problems if x is 0? What's the problem we run into? Where? What equation? The first equation? If x is 0, the first equation would become y times e to the 0 because of this, right? Equals the right side, which is 0. Which, if you divide both sides by e to the 0, which is 1, or just turn that into a 1, this means y is 0. I don't see a contradiction yet. So that's OK? So if x is 0, y is 0. But the third equation is going to fall apart. Look at the third equation. In the third equation, what do you get? 0 cubed plus 0 cubed equals 16. Not happening. Got it? So that's not going to be the case. So I can't let x be 0. If x is 0, I'm never going to satisfy the last equation. With me? Because in order to satisfy the first equation, I have to let y be 0 also. So letting x be 0 forces y to be 0, and as soon as that's done, the third one's never true. What else do we need to look at here? What is that? Y, what? Oh, suppose y is 0 or not 0? OK, suppose y is not 0. I'll do it back up here. Suppose y is not 0. What are you going to go for lambda in the second one? Is that what you're going for? No? Is that what? Didn't we solve for lambda in the first one? Yeah. Plugged it in here and then got all our stuff? What if we try and solve for lambda in that one? We're probably going to get the same thing. Suppose y is not equal to 0. Equation 2 becomes x e to the xy equals over 3y squared equals lambda. You following? Same sort of logic as before. OK, then number 1, from number 1, I can replace it's y e to the xy equals 3 times lambda, which is x e to the xy over 3y squared times x squared. Do y'all see this is exactly the same thing that's going to happen? Our 3's are going to cancel. The e to the xy's are going to cancel. I bring my y squared over x cubed. So I'm going to have y cubed equals x cubed again. Check. We've done that already, haven't we?
Do you want to show this separately? If we can see that the same thing is going to happen for when we're doing x can be 0.
Yeah, you can. You could just make sure you say, suppose y is not 0, and we're going to get the same result. Just make sure you state it, because I just don't want you to forget to check things, that's all. All right, what if y is 0? Suppose y is 0. Contradiction, right? We're going to not be able to get this one to be true. So that means we only have 1 point, right? What's going on then?
It's like another side.
Let's take a look at it. Something's going on here. First of all, this is, oh, well, I should erase some of that stuff, huh? I have the domain graphed separately here. That's your constraint equation. That's x cubed plus y cubed equals 16. Right there. That's what it looks like. If I plug just those points in to this, make one of these smaller. First of all, let's look at the domain on the ground. See the domain on the ground? If I plug just those points in, it's where this green thing intersects the surface. So I'm going to take that out. You see that? Got it? So just those points, and it comes in, it spikes up, comes back down, goes, right? What does it look like is happening? Looks like we have a maximum, right? But then here, minimum, do we have one? That's asymptotically approaching what appears to be 0. But it's never getting there, which means you don't have a minimum. See, our restriction equation, I don't know if you notice this, our restriction equation, which is this right here, is not a closed curve. It goes in both directions forever. So we're not guaranteed to have a minimum or a maximum if the thing goes forever. So we should only have a max. It should only be that point right there. And do we know what it is? Well, I can tell you where it happens. It happens at f of 2, 2. Is that what it was? And what was the function's value at 2, 2? E to the 4th.
How would you know that's the max instead of the min?
Good question. How would you know that's the max, not the min? Great question. Just try and find a point that, give me a value, any value, that would satisfy that. Just give me anything. Make it simple. 2 and 2? Okay, so 2, 2 lives on that curve, right? Plug 2, 2 in there. Oh, that's, hold on. Other than the one we just, yeah, sorry. How about, no, 1, 1 won't work. How about,
Isn't this Bernard's theorem?
what?
There's no
Oh.
there's no nice answers, or there's no whole number answers to
Yeah, but I wasn't saying we had to use whole numbers. Yeah, I was thinking y'all would just like plug in 0 for one of them, right? And then just give me like cube root of 16. Like I thought that's what you would do. That's okay though. 2, 2 works, but we already checked it. The point is this. You don't know if this is the max or min, right? So if you pick any other point on the curve, if this is a max, that's going to be smaller. If you pick any other point on the curve and the point when you plug it in is bigger, then that's a minimum. So all you have to do is check one other point. So what happens if I plug that in? What's f of 0 cube root of 16? That's e to the 0, isn't it? Which is 1. So 1 is definitely smaller than this, so this has got to be a maximum. Thank you for asking that question. I would have forgot to point that out. So it's a max. All right. Doing good, doing good.
How do we know what point to pick? Anything?
Any point. Yeah, it has to satisfy the constraint though. In my notes, I actually worked out the work for that one. Oh, look, I even did a point. Oh, see? To see if it's max, to find a point, satisfy 3 that yields a smaller value, plug in. See, I even use 0 cube root. I forgot I put that in there. Okay, let's look at this one. The reason why I'm going through all these, and of course I could let you do these on your own, is because each one of these, the algebra is just, a little bit different. And all right, I'm going to go through. I'm going to set this up a little bit quicker. Let me remind you, this is x to the negative 1 plus y to the negative 1. That this is x to the negative 2 plus y to the negative 2 equals 1. That's going to help me when it comes to derivatives. So my first equation is going to be what? Negative 1 over x squared. Is it all right if I do that? Yes? Equals lambda times, maybe I should put negative lambda. What? Negative 2 over x cubed. So how about I do this? Negative 2 lambda over x cubed. Second equation, negative 1 over y squared equals negative 2 lambda over y cubed. Pretty much identical, isn't it? And then the third is the constraint. Any ideas here? I can multiply, how do you mean? Like, do like a cross multiply, like this?
Or simply just multiplying the cubed onto the left side will give you x.
Okay, yeah, I see what you're saying. So multiply here, both sides by x cubed. Multiply right here, both sides by y cubed. They're both negative, right, on both sides? So now if I multiply both sides by x cubed here, I have to promise x can't be 0, right? But do I need to worry about that at all? I don't even need to state it. Why? It's not even within the domain of the original function. So you're never even going to be able to talk about x being 0 or y being 0 to begin with. So I don't have to tell you, suppose x isn't 0, because then I would look like a fool, right? Because then I'm telling you to don't consider a point that's not even in the domain. So I'm just going to say here, from here, multiply both sides by x cubed. I get x equals 2 lambda. Over here, y equals 2 lambda. Hey, that's nice. That means x is y, right? X must be y. So suppose x is y. What can I do with that?
Plug it into the third equation.
Go into the third equation. The third equation would turn into 1 over y squared plus 1 over y squared, or you could say 1 over x squared plus 1 over x squared. Either way, right? Equals 1, which means 2 over y squared equals 1, which means y is equal to plus or minus the square root of 2. I'm just moving things around. Also, I multiply both sides by y squared here. Y can't be 0. I didn't need to state that. All right. I should be able to get 2 points from this, right? I know that x must be y, and this is what y has to be. So I can have, continuing still in here, I can have root 2. I could have negative root 2, negative root 2. I need to try and get lambdas for those. I think the lambdas are going to be pretty easy to get, right? If I solve both of those for lambda, just our x coordinate divided by 2, or the y coordinate divided by 2. But since the x and y are the same, this one will be root 2 over 2 and then negative root 2 over 2. So far, just two points that I need to consider, right? Any questions? Is there anything else I should do that's going to give me anything different? I don't see anything else, right? I mean, if I solved these both for lambda, I'd get x over 2 equals y over 2, which is still x equals y. I think we've covered it. Well, this one looked bad in the beginning, but it's turning out to not be that bad. We all right? Let's go for it. Let's see. What's f of root 2? 1 over root 2 plus 1 over root 2, which is 2 over root 2, right? Which is just, if you rationalize the denominator, is just root 2. And then the other one is just that, but negative, right? So it looks like we have a max and a min. This one has a really cool picture. That's why I wanted to show you this. May I erase? "20 minutes. Okay. This is the surface. Really kind of cool looking, right? X can't be 0, y can't be 0, right? So the entire x-axis and y-axis are gone in this picture. If I plug in the domain, that's your domain, okay? That's what it looks like. So it's really a cool domain. If I plug it into the curve, there it is on the ground. And now I'm going to plug in those points into the function. And you can't see, it's the black stuff. Boy, that's hard to see. Let me pull the function back a little bit. I don't know if you can tell. Can you tell? This curve right here is getting plugged in, and it's going right up here onto this piece. So what we figured out is that there were 2 points. Let's see. There's one of them. Okay, there they are. Check that out. There's one of them. There's the other one. We satisfied? You're going to have to get in here and get your hands dirty with the algebra. But now what we're going to do is we're going to extend this now. This is the beauty of Lagrange multipliers. It does not matter how many variables your function has. So if you have a function of 3 variables, subject to a constraint equation that contains 3 variables, you can find the maximum and minimum also. The equations are exactly the same. You set the gradients equal to each other, lambda, and then you satisfy that last one. So how many equations will we have? 4. Partial of f with respect to x equals lambda partial of g with respect to x. Partial of f with respect to y equals lambda partial g with respect to y. Partial of f with respect to z, which we didn't have before, equals lambda partial g with respect to z. And finally, the constraint equation. So those are the equations. Yes, y'all follow? Everyone said like in unison 4, so those are them, right? Okay, so what I'd like to do, is there anyone else who's already done the bonus question from last class? One person turned it in. Do you have it to turn in?
Yeah.
Yep, I'll take it right now. I'm going to do this problem. And then the problem's no longer offered for bonus.
Oh, wait. Oh, you said one bonus question.
It was the one, no, okay. The one with the rectangular box inside the ellipsoid. Remember that problem from the end of last class? Was it fun? I see it took you a little while. Well, the derivative was okay. Okay, so what I'm going to do is I'm going to go back to last class. which, if I can find, here it was. It was this problem. Do you remember that? We were trying to get the largest possible box inside this ellipsoid. And when we worked through it, we actually came up with a pretty good idea of what we needed to do. We needed to find the maximum of this volume function we came up with. It was volume was x, y, z. Right? We need to find the maximum of that. And what we knew is that we were restricted to this ellipsoid, right? Yes? So what we had to do last class is we had to try and use the methods from 11.7, but the methods of 11.7 required that our function be a function of two variables, right? So what we did is we took this and we solved it for z, which gave us this ugly square root, and we replaced it in here, and then we had a function of two variables and we were in business. And it was a nasty derivative and the algebra got ugly. What I'm here to show you now is that this is perfect for Lagrange. We have a function f, we'll call it f even though it's v. This is f of x, y, z, yes? But that x, y, z just can't be any x, y, z. It's constrained, right? The x, y, z must live on this ellipsoid. That's the constraint equation. Understand? I want the maximum of this constrained to this. This is our g. Oop, overshot that a little bit. That's our g. So let's try and set this up. What would the first equation that we have to solve be? Oh, it was 8. Thank you. Yes, it was an 8 in here. I'm glad you reminded me of that. It was 8 because the xyz was just in the first octant. Thank you. So what is the first equation we're going to have? Because we're going to have 4 of them. Pardon?
Do we have to consider that
Have to consider what?
in this situation?
The 8?
The 8?
It's not, the x, y, and z that make it the max will be, the 8 won't matter. The actual maximum volume, we need the 8. But to get the x, y, z, it wouldn't matter. But it says, see, it says find the volume though. So if you left the 8 out, just remember to multiply it by 8 at the end, yeah. Okay, first equation is the partial of this one with respect to x, right? Which is 8yz equals the partial of this with respect to x, which is, and then lambda, 18 lambda x. Yes? Second equation is 8xz equals, 72 lambda y. Y'all with me? Third equation. 8xy equals 8 lambda z. Fourth equation is the constraint. Okay. 4 equations, 4 unknowns, x, y, z, and lambda. What do you want to solve for? My goodness, that looks crazy. There's different methods you could use here. But I want everyone to notice something. 8yz, 8xz, 8xy. Those are almost the same thing, aren't they? Like, if this was 8xyz, and this was 8xyz, and this was 8xyz, then they would all be the same, wouldn't they? And I could set them equal to each other? So how would I make this one 8xyz? Multiply both sides by x. But then I have to tell you, make sure that what? X is not 0, right? Now, am I going to be concerned about that? Like, am I going to need to go back and check it, what about when x is 0? Yeah, you would, but think about your volume. What's your volume if x is 0?
0.
So who cares? We know that that's not going to be a point, right? We know that that's not going to give us a maximum volume. So same thing with y. What if I multiply both sides by y here? Then I have to say, suppose y is not 0. But if y is 0, then I'm stupid to be looking for maximum volume when y is 0. What about here? Multiply both sides by z. Z can't be 0. Well, I hope not, because then no volume. Understand? So I'm going to quickly eliminate the whole idea of x, y, or z ever being 0. All right? Who cares? So I'm going to multiply this by x, which gives me 8xyz equals 18 lambda x squared. This equation, I'm going to multiply everything by y, so 8y xyz equals 72 lambda y squared. And then this equation multiplied by z, xyz equals 8 lambda z squared. All right. Now, if these are all 8xyz, right, then I can set any two equal to each other. So how about setting this one and this one equal to each other? How about that? What if I do that? What if I set 18 lambda x squared equal to 72 lambda y squared? How about we move everything to one side? 18. Do y'all know where I got this from? Yes, everyone okay on that? No? Yes? No? This and this are the same, so I'm setting this equal to this. So this is 18 lambda x squared minus 72 lambda y squared. Factor out a GCF. It's the biggest number I can get out of there. 18? Lambda? What am I left with? X squared minus 4 y squared equals 0. What are the two possibilities here? Lambda is 0, right? Lambda could be 0, or what? X squared could equal 4y squared. So I could set that equal to 0. Now I'm going to have to look at both of these scenarios. But I'd like for us now to just think about this. Look at equation 4. Do you see I can replace x squared with 4y squared? Maybe there's a way that I can get this z out of here and put y's in instead. So set which ones together? This time, set this one equal to this one, because that has y's and z's, right? So I'm just saving my thought right here, and I'm going to now set those two equal to each other. 72 lambda y squared equals 8 lambda z squared. Move everything over to one side again. 72 lambda y squared minus 8 lambda z squared equals 0. Factor out a GCF, which would be 8 lambda. And you're left with 9y squared minus z squared, which would mean what two things for you? Lambda is 0 or 9y squared equals z squared, right? Okay, let's go and write equation 4. Write equation 4 down. We're going to let x squared be 4y squared. We're going to let z squared be 9y squared. So from equation 4, we have 9 times What's 9 times x squared? What's that going to give us? 36y squared plus 36y squared again, plus what is 4 times z squared? And 4 times z squared is 9, so another 36y squared must equal 36. Which means we can, what, just divide everything out by 36? So 36s are gone. Those turn into 1s. 1, 1, 1. So you get, how many y squareds on the left? 3 of them. 3y squared equals 1, which means y equals plus or minus the square root of 1/3, which is plus or minus the square root, 1 over root 3. Which we only have to look at the positive. Because if you remember when we were doing the problem, the x, y, z that we were picking was in the first octant. So all the coordinates were positive. So all we have to do is look at the positive case here, okay? If I know what that is, if I know what y is, can I get x? Yeah. Just square that. Square it. What do you get? 1/3. And then multiply times 4. 4/3, then take the square root. So be back at 2 over root 3. I know I'm working quick because we're almost done with this. And we're almost done with class. So from that information, this right here implies that x would have to be equal to 2 over root 3. And finally, you could get z. What would z be?
If you square that, wouldn't that be just 3 on the bottom?
Well, hold on, because what we're doing is we're going 4, and then what's y? It's 1 over root 3? But then you're squaring it, right? That's what x squared is. So that becomes 4/3, but then square root again, and it goes back. What is this? What is it? 3, root 3. So it looks like 2 over root 3, 1 over root 3, and the z coordinate root 3. I don't want to put you on the spot. Do you remember if you got that? You did get that? So I don't know if you think that was quicker or not.
Yeah, it looks like it was quicker.
Yeah.
A lot cleaner.
Lot cleaner. Lot cleaner.
Is it because of the, when you were talking about we only look at the positive because it's in the first octant, could we just say because the volume couldn't be negative?
Yeah, same thing.
Is that
That's why we were saying first octant. Yeah, because we don't want to go negative volume. Now, we did need to look at, what if lambda is 0? But if lambda is 0, look, if lambda is 0, this is 0. And that means this is 0. And that means this is 0, right? Or even better, you could go up to this one. 0 here, 0 here, and 0 here. So look at this. What does this mean? Either y is 0 or z is 0. And if y is 0, you have no volume, right? Who cares? Here, same thing. So lambda being 0, although there might be some values, it's not going to be a maximum. So within the context of the word problem, it wouldn't make sense for you to go look at those. All right, well, we have 5 minutes. I think this is a good time to cut off. The homework assignment for this one is, I think it's incorrect. That's not even the right page. Yeah, that's not supposed to be there. So that's supposed to be... And I have not done these. I started working on these the other day. I just haven't gotten to them. Anyone want to tell me what page? Oh, wow. Oh, yeah, hold on. That's correct, probably. What I meant was the 11.8 homework. We will do some more. We will do some more. But please, if someone could check, does anyone have their book? 683? Yeah, 11.8, 683. This should be just 1 through 19 odd. So I have like 2 minutes left, right? For any of you who actually use these interactive CDF players that I've made, I know you use them, right? Someone does? Does anyone? Because if no one does, I'm not gonna, okay. If anyone, I actually put something here at the end that you may find useful sometime later in your life. I made these calculators where you can put in, like the problem we just did a second ago. Remember where we had that plane? F of x was 4x plus 6y. And it was constrained to that circle, x squared plus y squared was equal to 13. If you type the function in, the constraint function, and then the constant, and then you go and you hit this little U button, this program will actually go through and find your optimum solutions, your x, your y, and your lambda. It'll actually do it for you. And then if you want to do it where you have a function of 3 variables, this is the problem we just did. Wasn't that the volume? Wasn't that the volume right there? 8x, y, z. Wasn't the ellipsoid 9x squared plus 36y squared plus 4z squared equals 36? And you go through this and look at, I mean, it's spitting out a bunch of shit here, but it's giving you a bunch of the zeros. And see, it doesn't know that we're positive or negative. So it gave us some negative values in here. But this is the one right here. Where is it?
9.23.
Oh, yeah, because these are both negative, that would work also. There's more answers. There it is. This one right here is the one that makes the most sense to. Oh, no. Where is it? X, Y, Z, all positive. I'm missing it.
I think it should be the last one. Needs more room.
Yeah, the last one has that x equals -2.
Yeah, it's probably that. But it's,
Huh. You know, there might be something in the code that prevented it from doing that. I can go back and look at it. I might have limited the number of answers it spits out. I don't even want to see this code. It's been so long since I wrote it. I don't even remember. It's not that much. Okay, well, either way, it's pretty good, okay? I mean, you can tell I was a little off. What we're going to do next time is we're going to realize that there's a way we can use Lagrange when we have a function of 3 variables with 2 constraints instead of just 1. Yes? Oh, yeah. So what are we going to do for the midterm as far as note cards or cheat sheets or whatever? Okay, you have the formulas that are off of our website, right? Those pages, no? In Canvas, the standard calculus formulas. They're 8 pages. Just check Canvas. I'll put them up there after class in case they're not there. Standard 8 pages of integrals and derivatives and trig stuff. I'm just trying to decide, do I want to reward you, give you bonus for not needing any note cards or penalize you for needing them? Okay, then here's the deal. One sheet, front and back, formulas, steps, procedures, no worked out problems. Okay? So you may have the formula sheets that I will provide you. Okay? In addition, one sheet of paper, front and back. You can write whatever you want. No worked out problems. Formulas, steps, procedures. That's it.
Do you have to write? Can you write on something and print it?
Oh yeah, you can. Yeah, you can do. Just don't come in and be like, I need a magnifying glass to see this. Can I have my magnifying glass? Because you have to be able to read it yourself. Okay. So everybody gets that. If you don't use a formula sheet, then I will reward you. I don't know yet. Let's see how many people don't need them. Like if you're the only one who doesn't use a formula sheet, I will reward you more than if all of you do.
What do you want? Like it's 5 points.
Take it or leave it. I'm not telling you how much. Yeah. Okay? Everyone clear on that? One formula sheet. That's it.
I did all 40 and then you got like +6.
Y'all have a good day. I will. Yeah, I'll be in there normal time, which is 9 till, I think my first class is at 11. Yeah. What do you mean? Well, on Wednesday again. Are you saying like tomorrow afternoon, or are you saying no more on